Today I'll be talking about the prediction of crop yield for the past or the future, testing machine learning for yield forecasts. I am Francisco Villalobos and I work at Instituto de Agricultura Sostenible and the University of Cordoba in Cordoba, Spain. First of all, we have seen a lot of papers using machine learning in the past 20 years applied to many problems in agriculture, including yield prediction. But first of all, what do we mean by prediction? We made use the statistical sense where prediction is the same as estimation, and it refers to a static concept related to the present or the past. And that means transferring knowledge about a given sample to a whole population. In other words, we would be interpolating from the knowledge of a few individuals to the whole population. As opposed to that, when we talk about forecasting, we are meaning something dynamic, where we take a sample in the past and try to know something about the population in the future. We could say that now we would be extrapolating. This is an extremely important application as we need forecasting for management of crops, but also for the formation of prices or for food security. In many cases, the lack of predictive power of biophysical models have turned people to try to use alternatives like machine learning. Why this lack of predictive power? Well, some of the reasons are the incorrect or incomplete formulation of the biophysical model. Many times we still lack knowledge to build a powerful model. In other occasions is an incorrect calibration, because experiments to do calibration are expensive. In other cases is the lack of input data or errors in the input data, which might make the model work incorrectly. Also, the observed data used for testing the model might be somehow in error. The alternative that has been used in the past for yield prediction, in many cases in the statistical sense, is the use of empirical models. And that has included multiple linear relation, including the possibility of regularization, like in the lasso or ridge methods, where we try to minimize the root square of the sum of the errors. We add a penalty function which is proportional to the absolute value of the coefficients. This regularization allows the model to be reduced to the most meaningful parameters, so we can discard variables from the model. We can also turn to nonlinear regression, but what we have seen spreading in the past 20 years is machine learning or deep learning. There are different ways of naming that, with special attention to artificial neural networks, to the classification and regression tree, the CART, that is expanded to the random forest. In a broad sense, machine learning is a set of mathematical machines used for building data-driven models for prediction and decision making. And they can deal both with qualitative and quantitative data. In fact, they started basically for qualitative analysis, for classification problems, and later they became more adapted to quantitative regression problems. The application to regression was focused basically on the use of artificial neural networks to the cart or to the random forest. If we think about regression, the great advantage of these techniques is the so-called universal approximation theorem. There are many versions of this theorem, but basically what it tells us is that a single hidden layer artificial neural network can approximate any continuous function. So an artificial neural network, if we add enough elements, will be able to approximate any continuous function. So it is powerful in terms of representing any type of model. In fact, most papers have used artificial neural network in the yield prediction problem. In this work, we have tried to analyze the capability of machine learning for yield prediction for sunflower and wheat using a synthetic dataset obtained with crop simulation models from DSSAT. And we have tried to establish guidelines for the fair use of machine learning in crop yield prediction or forecast. First, we created a synthetic datasets of yield of sunflower and wheat in 4 areas in Spain. In each area, we define a set of farms, each of one differing in size, in soil depth and texture, in management, which include in sowing date, nitrogen fertilizer, irrigating or not irrigating, the cultivar, and the 5 areas that we consider were scattered from the southwest of Spain to the east of Spain. From Lobón, which is almost 39 degrees here, to Belmez and Cordoba in Andalusia, then Baza, eastern Andalusia, and then Castellón, close to Valencia. The coldest place is Baza, with a low rainfall. The highest rainfall occurs in Cordoba. Mildest temperatures occur in Castellón. The mean rainfall was between 370 in Baza up to 611 in Cordoba. And the standard deviation of rainfall was quite high, so we had a coefficient of variation between 25 and 30% for annual rainfall. We performed the simulations using Ceres wheat and oil crop sun in DSSAT 4.8. We use weather data from 2001 to 2020 in one weather station in each of the 5 regions. First of all, to apply machine learning, we have to define the so-called features, in other words, the input variables, which after some preliminary analysis resulted in sowing date, amount of nitrogen applied, amount of irrigation applied, anthesis date, rainfall in the preceding fallow plus the growing season, mean maximum temperature and mean minimum temperature, mean solar radiation during the whole growing season, average soil depth in the farm, year, and cultivar. These 11 variables were used as independent variables for fitting the models. We also assumed that there was a cultivar change around 2010. The cultivar change started in 2008 and ended in 2012. In the case of sunflower, the farmers changed from a short season cultivar AE353 to a semi-dwarf cultivar which is a Sunwheat 101. In the case of wheat, we moved from a standard spring wheat, typically grown in the area, to an isoline here that had as an only change the number of grains per spike. So that meant a 20% increase in the number of grains. The simulations showed a wide variation in yield both for wheat and sunflower. This is wheat in the 5 regions, and we see yields with years with almost no yield at all, up to close to 5 tons per hectare in the case of Lobon. In Lobon there was some supplementary irrigation up to 100 millimeters, so that showed the highest yield on several occasions. The variation in Cordoba was huge. We had 1 year with almost nil yield, and 1 year, a couple of years, several years with more than 4 tons per hectare. For sunflower, we see a similar situation where the highest yields occur occasionally in Lobon, as we had some supplementary irrigation, and the lowest yields occurred in Baza, in the province of Granada, eastern Andalusia. We see also a wide variation in yields, going from almost 0 to more than 4 tons per hectare. There is no possibility of comparing these synthetic yields with actual yields, but we can have a look at the statistical yields at the province level in Cordoba or Granada. Look at Cordoba, for instance. This is the period from 2001 to 2020, and we see that the average and standard deviation in the Cordoba province are close to the simulations in the Cordoba location. The same goes for sunflower in Cordoba. In the Cordoba province is similar to the simulations performed close to Cordoba. And for the test set, the root mean square error is 37, and then the best method are random forest with 6 and an artificial neural network with 2 cells in the hidden layer with 24. So for wheat, there would be an advance. The machine learning methods would yield a good result. If we go to the test, we see also that the machine learning is performing good. The same goes for sunflower. Both for the train and testing, there is an improvement using the machine learning methods, both random forest and artificial neural network. In fact, random forests tend to be better. Remember, we are now using random partitioning of data. What happens if we don't break up the data but use first the first 15 years for training and then 5 years for testing, like here? This is for wheat, and we see that for the train we have a good performance, but then for the test, the root mean square error for the machine learning methods is very close to the best guess using just the average of the farm. So here, for wheat, the partitioning shows that the machine learning methods are not performing much better than the best guess hypothesis. The same goes if we think about sunflower. If we go directly to the test, we see that the root mean square error is 42 using the average, and is 54 using the best artificial neural network, and 33, which is not too far from the root mean square error obtained with the average. If we use only 5 years for training and 5 years for testing, as in this table, in this case is for wheat, as we typically see that in the training phase the models are good, but in the test the models are not, in this case, not far from the best guess hypothesis, and in this case much worse. They can be much worse than the artificial neural network. Something similar happens for sunflower. So we are not seeing, when we do the partitioning of data using first the data for the past and then we test with data from the future, then we don't see much a good performance of the machine learning methods. Although have not been pointing that multiple linear regression performed poorly and regularization had little effect on the results. So not machine learning, not multiple linear regression had a good performance. For yield forecasting, we have seen the artificial neural networks were not better than the best guess hypothesis. In other words, using the average in the farm. And then the random forest is slightly better than the average, and then we should wonder if the cost of getting the data would be worth it to use artificial neural networks for yield prediction. The results indicate also, or some of these results have to be put in context about the renovation time of cultivars. For instance, in the case of wheat around the world, the average time for renewal of cultivars is around 7 years, and only 5 years in Western countries. That means that the cultivars are renovated in short periods. So that means that no cropping system stays the same for too long. In practical terms, that means that we'll be limited in the length of the training data sets that we can get for crop yield prediction. We have to emphasize that random partitioning of the train and test data will only be valid when we want yield estimates in the past. In other words, when we are dealing with interpolation problems. That can be interesting, for instance, if we are testing farmer declarations on yields and we want to have a model that allows us to detect farmers that are out of the normal rule. But random partitioning is not valid for the future when we are doing extrapolation of future yields. In other words, when we are doing forecasting. Machine learning models for forecasting require long series to ensure enough data for training. And we wonder if under regular conditions, under normal conditions, we'll be able to have these training data sets long enough. Thanks for your attention. And if you are interested, you can have a look at our paper published in Frontiers in Plant Science, using machine learning for crop yield prediction in the past or the future.